A very good afternoon to one and all. And today concept is about learning a new parsing technique, that is LALR parsing technique. And what the LALR stands for here. LALR is nothing but an look ahead LR. Sometimes you can call it as an intermediate LR. And after knowing the parsing techniques about the LR of 0 and LR of 1, the last parsing technique under the LR parsers, that is an LALR parser. That means it is an look ahead LR parser. And here in this type of parser, the look ahead symbol is generated for each set of items. And the same thing that we generated in an CLR parser also. And here the table is obtained by this method are smaller in size than the LR of K parsers. And here in the states of the SLR and the LALR parsings are always to be same. Whatever the states that we are generating in the SLR and the LALR parsers, are always to be same. That means when we are comparing the SLR and the LALR, comparing in the sizes, the both the methods are smaller in size. And here most of the programming languages uses LALR parsers. And whatever the steps that we followed when we are constructing the CLR, that is LR of one parser, the same steps that we are following here. See, once I'm recalling the LR of 0 and LR of 1, in the construction steps of both LR of 0, that is SLR, and LR of 1, that is CLR, the only one difference, the main difference is at the place of computing the closure of I, not only by placing with the dot operators, we are placing the look ahead symbols in the CLR. That's the main difference between the computation of closure of I at LR of 0 and LR of 1. And when constructing the parsing table, there what's the difference is in LR of 0, before to construct the parsing table we need to construct the first and follow table, but here in LR of 1 we are not constructing the first and follow table, just basing on the basing on the look ahead symbol, we are placing or filling the entries by using an reduce operation, isn't it? These are all the things that we already learned in the last classes when we learned in the concepts of LR of 0 parsing technique and LR of 1 parsing technique. And here what the LALR parsing technique is, whatever we done in the CLR, whatever the steps that we followed under the construction of parsing table or under the construction of go to and closure functions, that means initially we need to construct the closure, right? So under the construction of or computation of go to and closure, closure and go to, and under the construction of the parsing table, whatever the rules that we followed when we're constructing the CLR, that is an LR of 1, the same thing that we're processing here in LALR. Nothing difference is there. Nothing difference is there when we constructing in a step-by-step process. And what the difference, main difference is, here we are representing another table. We are representing another parsing table by giving a heading LALR parsing table. And how to represent that table? After construction of CLR parsing table, and from the table directly we are constructing the LALR parsing table. How to construct the table, what are the rules to be followed there, and what we are taking as a main constraints here, right? That's the question here, to learn the concept that is an LALR parsing. And here whatever the steps that we followed there in the SLR or in the LR of 1, that is an SLR is an LR of 0, in the both canonical LR and the SLR parsing techniques, whatever the steps we discussed there, whatever the steps we followed there, the same steps that we're following here. That means initially we're constructing, that means formatting the augmented grammar, and the second construction of the canonical set of items in LR of 0 without look aheads, in LR of 1 with look aheads, and then building the parsing tables and then parsing the input string using LR parsing tables. It may be an LR of 0 parsing table or LR of 1 parsing table, right? And these are the main important 3 steps that were discussed when we are constructing the parsings, LR of 0 parsing and the LR of 1 parsing. And here, what are the steps that we are considering, or what are the steps that we are following when to construct the set of LR of 1 items along with the look ahead in LALR parsing. That for that question the answer is, and here the construction of LR of 1 items is same as the construction of CLR of 1 items. LALR, whatever we are constructing, whatever the computation that we need to do for by using an closure of I and by using the goto function, it is both in CLR and LLR both are same. With the look aheads we are computing here with the look aheads, make a note. And but what the difference is, in construction of LALR of 1 items, we have differed the two states, right? We have differed the two states. That means if the second component is different, but in this case we will merge the two states by merging of first and second component from both the states. See here, we're having an example like in the previous example. See in the previous example. See the item number 8 and item number 9. See the item number 8 and item number 9. C tends to CC dot C by D. C tends to CC dot comma dollar. The rule is same. The production rule is same here. What's the differ? Look aheads are differ, right? And what we need to do is we will merge the two states by merging of the first and second components from both the states. Here I am considering these items as an states, right? These items as an states. So I am merging these two components from the both states. Now I8 and I9 becomes I89. After merging, I8 plus I9 is I89. Isn't it? Is it clear? That means we have got the two states like an I8 and I9 because of different second components. Second components are differ, but the first component is same in each and every rule there. But for LALR parser, we will consider these two states as same by merging these states like I8 plus I9 is equal to I89. I think you get. And with the example, I will clearly explain in further slides. See all of you. And why the LALR parsers are often used and often used in practice because LALR parsing tables are smaller than the LR of 1 parsing tables. And here the number of states in the SLR and the LALR parsing tables for a grammar G are equal. But LLR parser recognizes more grammars than the SLR parsers, and one of the property of the LLR is it is widely used parsing technique, and while coming to SLR it is easy to develop and simple to construct, and while coming to CLR it is most powerful parsing technique. And here we are implementing with an ACK tool, that is one of the building tool. In the process of compilation we are using two types of tools. One is an lex and another one is an ACK. For generating the parsers we are implementing an tool like an ACK tool. By using this tool we are creating the parsers, we are generating the parsers. And here this ACK creates an LLR parser for the given grammar. A state of LLR parser will be again a set of LR of 1 items. See, these are the main most important basic points about the LLR. What the LLR is, why it is often used, why the LLR parsers are often used, and while comparing the LLR with the SLR, in size both are equal, and comparing in sizes both are equal. That means both the grammars SLR and the LLR parsing tables for the grammar G, the number of states are equal in both the parsing techniques. And while recognizing more grammars, we prefer LALR. That means for complex grammars, we'll use the LALRs. And here we're implementing a tool like an ACK. With the ACK, we're creating the LALR parsers for the given grammar. By the hand, we are not implementing this. This is just knowing how the internal functionality was done, how it is going to be done, and what type of parsing techniques we are implementing here, and how the construction of each and every parsing technique is carried out, and what the steps that we're following there. And all these are all we are learning means by the compilers, we are not writing by the hand there. Right, I think you all understand what my intention is here. And as we know that by giving the input and expecting an output, the output was generated in a fraction of seconds, right? Within the fraction of seconds, with the tools, with the automated tools, the everything will be done. Everything will be done. It was not done by the human can't sit and write there, can't sit and write construct the parsing techniques like this is the process of learning what the techniques that the analyzer syntax analyzer consisting of. So for that we are learning all these concepts, for that knowing what how the implementation of the syntax analyzer is carried out, and the how internal functionality of the syntax analyzer is. And for that questions we are all learning these concepts under the syntax analyzers. But while coming to the process of compilation, these are all not visible to us. How the tree was structured, whether it uses a top-down parser or whether it uses a bottom-up parser, all these are all not known to us. It's just by giving an input and getting an output in the fraction of seconds what the how the process of compilation takes place internally with each and every phase, with each and every phase. And with by using with the automaton tools like this, by using with an automaton tools like this, just giving the variables, just giving the in the grammar consisting of that non-terminals and the terminals, right? And just by giving the terminals and non-terminals, the tree with that grammar, the tree was structured by implementing such type of parsing techniques. We can't see, it was not visible to us, we can't see what the type of parsing technique it was implemented there, right? And what here is, and just we are learning, we are knowing how to construct all these types of techniques. If we construct this type of an technique with such type of an grammar, then what type of an output that we are generating, the output is always should be an parse tree, right? After constructing the parsing table, then the next step what we done there, we implement the stack implementation means we, by taking an input string, just we pass that input string and we check it out whether the input string is acceptable for the constructed of steps or not, for the constructed steps in the sense for the computed parsing technique or not, right? So and after checking out the whether the input string is acceptable or not, if it is an acceptable, then we need to draw the corresponding tree structure for that. We need to draw the corresponding tree structure for that type of parsing technique. So the each and everything was done in internally without participation, without direct participation of an human here as a part of the compilation. But we are learning what the parsing technique is. In parsing technique, how many parsing techniques are there? For example, how many approaches are implemented in syntax analysis? Two types of approaches we are implementing, and what those approaches are, and top down and bottom up. In top down, what type of a technique, what type of a techniques that are implemented, so how the construction was developed there, how the construction was implemented there, what type of and steps that we need to follow if we want to construct the LL of one parser, right? That is predictive parsing. And while coming to the bottom up parsing, if I want to construct an SLR parser, what the steps I need to follow, what is the construction steps that I'm having there to be followed. Based on the construction steps and the algorithms, I am implementing the parsing technique of the LR of 0, right? And all these are all we are learning to understand ourselves, not for the process of compilation, right? By using tools like an automaton tools like an act lex and all those automatic code generators, by using such type of tools, internally the internal functionality was implemented within fraction of seconds. No no direct participation of human was involved there, and no human was sitting and writing and constructing the parsing techniques like this, right? Just what we are learning here is how the process was carried out, how the internal process was carried out, and what type of techniques that are implemented there. So we are learning, if we are having such type of a technique, what that technique is, what is the meaning of technique, why we are learning this technique, what is the need of using in the syntax analyzers, how the construction was carried out, what the steps that are to be followed to construct such type of an parsing technique. All these are all learning for ourselves, not for the process of compilation, and not for just by giving an input and not by just getting an output within a fraction of seconds, right? Is it clear now? And then and now I'm explaining you how to construct the LA-LR parsing. By knowing the construction of CLR parsing, it was well understand to you, because only we are doing here is just we are representing an parsing table. That's enough for LALR. That means construct the LALR parser for the given grammar. Take down that grammar, and whatever the things, whatever the steps that you followed in the construction of CLR parsing, same as it is, you follow all the steps. That means formation of augmented, computation of closure of I with lookaheads, and computation of goto function with lookaheads, and then parsing table of the CLR, right? And that means there we implemented 4 steps, right? And what the fifth step in LALR parsing is, again you need to draw another table now by putting an heading LALR parsing table. And see, with an example I will show you how to represent an parsing table for the LALR from the CLR table. See, here we're having a slide. That means canonical LR parser is directly yields an LALR parser. What we are doing here is, with the output parsing of the, with the output of the CLR, we are just representing an LALR. What the output means, here we are taking the parsing table, and that is acting as an input to the LALR parser to represent an parsing table. And here in between, what we're doing is we're shrinking of some states. Shrinking is nothing but a merging of the states, merging the states. And make a note of this. This, when the process of, when the process of merging or string process may introduce and reduce conflicts, may introduce and reduce conflicts in resulting an LALR parser, then we can conclude that therefore the given grammar is not an LALR, right? But it never produces and shift reduce conflicts. Here totally we are having 2 types of conflicts, right? Commonly occurred errors, we can call it them. And in that, shift one is an shift reduce, one is an shift reduce parser. Sorry, it is not an parser. One is a shift reduce conflict, and the another one is a reduce conflict. Is it clear, all of you? Shrinking of the states may introduce, when we merge some states, merging of the states, maybe there is a chance to get this type of conflicts. And what the commonly occurred conflict is an reduce conflict. But this, when we are doing this type of a process like a merging process, it does not produce a shift reduce conflict, right? Make a note of this. Now I'm directly explaining this with an example. See, this is already computed. Go to graph in the last class. For the construction of CLR, I considered the grammar s tends to dot cc, c tends to dot cec, c tends to dot d, right? For this grammar, now I am representing an table. Now I am representing a table. To represent a table, LALR table, first all of you open the CLR table. All of you open the CLR table, right? See, this is an LALR table, and based on the CLR table, I am representing the CLR table like this. This is a LALR table. All of you open the CLR table, which was already I explained in the last class. I think you all represent the CLR parsing table after performing or constructing the LR of 1 items, canonical set of LR of 1 items. Then finally you need to construct the parsing table, right? Based on the parsing CLR parsing table, now I am going to represent an LALR parsing table. See, in the CLR parsing table, I am having an action of 0 with C is, action of 0 with C is S3. S3. And before knowing what this S36, just go to the computations. Go to the CLR computations. See, I naught with C, it is different. And see here, I3, go to of I naught with C is having the three rules. With then look ahead symbol C or D. With then look ahead symbol C or D, right? And please check it out in item number 6. For the same rules, the second component is differ. The second component, that is an look ahead, is differ in I3 and I6, but the production rules are same in the both items, I3 and I6. See, here we're having a dollar, here we're having an C or D. That means I3 and I6 is having the same rules but the different look aheads. And that means how we're going to write this is I3 plus I6 is equal to I36. That means we're merging the states 3 and 6 into a single state 36. Make a note. Make a note there. I36. Make a note there. I3 plus I6 is equal to I36. Then finding out, is there any more? Is there any more rules like this? Is there any more states like this? C tends to D dot, and here the look ahead is in C or D. C tends to D dot, here the look ahead is in dollar. That means it is I4, I7. I4, I7. That means I4 plus I7 is equal to I47. Again, make a note. I4 plus I7 is equal to I47. Again, finding out, is there any more? See here, I8. C tends to CC dot C by D. And in I9, C tends to CC dot dollar. In the both items, the rule is same, the production is same, but look aheads differ. That means I8 plus I9 is equal to I89. Make a note. I8 plus I9 is equal to I89. Checking out, is there any more items like that? No more items, because I3 and I6, I4 and I7, I8 and I9. From the go to computations, we get the similar production rules with a different look ahead items. We're calling them as states. That means what it means is shrink of states. We perform the shrink process here. That means combining two states, combining or merging two states into a single state. Here, those are all the items. Items, we are calling them as in states, right? Now, LALR parsing table. This overall computation is same as in CLR computation. That means whatever we done the go to function construction, that is same in LALR. Nothing is differ. Only at the last table we are considering, we are representing the last table. The table name is an LALR parse table. Before that, we need to represent an CLR, and from the CLR it is very easy to identify to represent an LALR table. See, that is I3 plus I6 is an I36, right? And previously in CLR table with 0 and C, there were having S3, right? But it was named as an S36. Why? Because S3 is merged to the S6 and item 3 is merged with an item 6. So now it can be called as a single state I36. So in place of I36, we need to write an S36. And same as I4 is merged with an I7 or I7 is merged with an I4, whatever it may be. Then the state becomes an, the item becomes an I47, right? So in the place of S4, we are writing S47, right? And here how many states are having in CLR table? 0 to 9. But while coming to the number item number 3, 3 is merged with an 6. So 36. 4 is merged with an 7. 47. No need to write again 6 and 7. Right. No need to write an again individual number 6 and 7. And 5. Then 8 is merged with a 9. It becomes an 89. Right. Is it clear now? That means wherever you are having the uh, shift operation with the 3 or 6, it can be written as in 36. We are having 4 or 7, like we are writing like this 47. It may be 4 or 7 or 7 or 4 or 6 or 7 or sorry, 3 or 6 or 6 or 3, whatever it may be. What it means is initially from CLR table here we are having an 3, but at 2 comma C we are having an 6. That means in the both places we are representing S36 and S36. And here we're having S4 in CLR table. We're representing with an S47. While coming to the while coming to here, the CLR table, item 2 with D is an S7, but here it is an S47. Right? Is it clear? After merging the two states, two items, no, there is no problem that if you are having only 7, only the 7 you need to write. There is no more questions like that. If you have 7 at anywhere, you need to write it as an 47. If you have 6 in anywhere, you have to write it as an 36. Or if you have 3 in anywhere, you have to write it as an 36. Or 4 in anywhere in the table, you have to write it as an 47. Or 8. See here, we're having the 89. That means 8 is merged with an 9. So at I3 in CLR table, I3 with C is an 8, and something I6 with C is a 9, right? So it is merged as an 89 because 3 and 6 now combined. 3 and 6 are merged now. It is in combined state now. So we're calling it as a single state. So we're directly writing like this. Directly writing like this. At 36, I36 with C, it is an 89. Right? Is it clear now? And while coming to these are the reduce, go to action filling of the go to column, and now action column filled with the shift operations, and 1 comma dollar is always accept, 1 comma dollar is always accept. And how to write the reduces, how to write the reduces means, see here in the previous table I4 I4 with C and I4 with D is having R3, and where this 4 is merged with N7, right? And for I7, it for the, at the place of dollar it is having R3. What it mean? In the single row we are writing R3, R3 and R3. That means 4 is merged with 7. 4 is combined with 7. That means we done and merge. We perform the merge operation here. 4 is merged with 7, and as per the CLR table, for only the 4 we are having at C and D R3 R3, and as per the CLR table only for 7 we are having at $R3. Now these 4 and 7 are combined together as a single state. So we are representing in a single row like this. We are representing the reduce operations in a single row like this. See, for 8 in CLR, for 8 at C and D it is an R2. For 9 it is an R2 at dollar in CLR table. While coming to LLR table, this 8 and 9 are merged together. So in a single row we are writing those. Those in the sense the reduce operations for C and D for the 8, and the reduce operation for the dollar, reduce operation under the dollar for the 9. Is it clear now how to represent an LLR parsing table? It's very easy, very simple to construct the parsing table. Directly after constructing the CLR canonical set of items, and after constructing the CLR parsing table, then the last thing what we need to do is we need to construct the LLR parsing table. And this is the way of constructing the LLR parsing table, just finding out which items consisting of, because every item is having two components. One from the first component from the rule, that means in from the grammar we are taking that as a rule, and the second component as an look ahead symbols. So the first component should be an same and the second component should be an differ. If we have such type of an items, taking those items and we are merging those, and uh, taking it as an as per the, as by considering it as in two states, two items, and after merging it is considered as a single item, that is a single state here. Right? Is it clear? This is the construction of LALR parsing table. And with this concept, the types of parsing techniques in LR parsers are completed. And here, as I said in the previous slides, that when we done such type of an process, that is a string process, may introduce and reduce conflict, may not produce and shift reduce conflict. For that we are having an answer. See here, for example, we are having an item number 1 with these rules and item number 2 with these rules. In the both item 1 and item 2, the first component is same, that is First component A tends to alpha dot. Here also A tends to alpha dot. But what the differ? Look aheads are differ. In second rule, first part is same. The look aheads are differ. Here B and there C. That means what we are doing? I1 plus I2 is merged as I12. I12. I1 plus I2 is merged as I12. So, and how we are writing this? Alpha dot. Here A, here B, right? Or B. And B or C. That means when we are filling the entries in the parsing table where we get an conflict like this. What the type of conflict is? Reduce conflicts. Reduce conflicts. Why? Because at I12, at item number 12, A tends to alpha dot is having a look aheads of A or B. That means both the rules are ended. Both the rules are ended. That means the dot was processed at the end. So when we are considering the follow of A for this and when we are considering the follow of B for this, and at the places of filling the entries in the both look aheads we are having B. In the both look aheads we are having an terminal B. So in such type of conditions we get an conflict like an reduce conflict. And the LALR parsers never, when we are processing and string process like that, shrinking the states, the process does not produces the shift reduce conflicts. The process does not produces the shift reduce conflicts. Make a note of this. And with this, the bottom up parsing concept was completed, right? And all of you make a note of this example, example number 2, and you please all construct the LALR parsing table for the given example. Consider the given example, construct LALR parser. Note down that example first, all of you. Consider the example. Consider the given grammar. Construct set of LR of 1 items for LALR parser. Construct set of LR of 1 items for LALR parser. Note down that question. Now, after completing the 3 types of techniques, after knowing about the construction steps or whatever the algorithms that we followed when we implementing the parsing techniques, then finally I need to compare these 3. Finally, I need to compare these 3. And initially I comparing with the size. And with the size, the comparison with the size in both SLR and LALR, LLR, that means SLR is nothing but an LR of 0 and LR of 1, that is a CLR of 1 and LALR of 1. And the SLR is smallest in size, and while coming to the LALR, both SLR and LLR have the same sizes, and CLR, where it is most powerful LR and very large in size. While comparing these 3, comparing these 3 with the size, the CLR is having an CLR is largest in size while comparing with an SLR and the LLR, right? Both are equal in size. That means SLR and LLR are equal in size. And the second one is we are not constructing any follow function for the CLR and the LLR. Only we are constructing in an SLR. That means LR of 0. And what the next thing is time and space complexity. We need to talk about the time and space complexity, and it requires less time and less space for the LR of 0. And while coming to the LALR, it is efficient in method. That means whatever the construction that we are implementing for the LALR parsers, we are directly implementing that. We are directly using that. So here also the time and space complexity is more, and in CLR parser the time and space complexity is more. That means only for the SLR it is less. For the both CLR and LALR, the time and space complexity is more. Why? Because those two comes under the LR of 1 parsing techniques. and SLR is an LR of 0 parsing. And the second one is in detecting of the errors. That is another most property to compare to how to detecting of the errors in these three types of parsing techniques. That SLR parsing technique, error detection is not at all an immediate action to be performed in SLR. While coming to the LALR, here also immediate action is not going to be performed. That means immediate error detection is not going to be performed here. And while coming to the CLR, immediate error detection is done by the LR parsers. That's why it is most powerful parsing technique. We're calling it as an most powerful parsing technique. Is it clear? And with the size and with the time and space complexity and with the considering the constraint like an error detection, these are the most important properties when we need to compare these three. Comparing with these three constraints, one is with size, one is with time and space complexity, and the another one is an error detection, finding out the errors. These are the most important points that we need to know after completion of the parsing techniques, that is an LR parsing techniques. Right, finally which one is most powerful and which one is better? Finally, CLR, that is an canonical LR of 1 parsing technique is a most powerful parsing technique. And for complex grammars, more complex grammars, we are preferring that the CLR parsings. And also for large classes of grammars, we mostly preferable for the CLR parsers. So finally, the efficient parsing technique between these three is an CLR parsing technique. Every parsing technique itself, it is very efficient one, but by considering some constraints like this, finally we are concluding that CLR parser is the most powerful parsing technique. And then we're having another small concept, that is from the starting of this unit number 2, unit number 3, that is on syntax analyzers. In 2 and 3, half of the unit is about the syntax analyzer in third unit. And both, while considering unit 2 and unit 3, at the starting class itself, I am saying that whatever the grammars, to implement such type of an parsing techniques, to implement such type of an approaches, the grammar should be an unambiguous grammar. From the starting class itself, I am saying the same thing. Whatever the grammar that we chosen for implementing a parsing technique means that grammar should be an unambiguous grammar, right? And here what the question is, if we are having an ambiguous grammar, can we construct the SLR parsing for that ambiguous grammar or not? Yes, we can construct the parsing table. Yes, we can construct the LR parsing table for the ambiguous grammar, right? But make a note of that all grammars used in the construction of LR parsing tables must be an unambiguous grammars, right? And we can create LR parsing tables for the ambiguous grammars. How? But they will have some conflicts, right? If the construction of the table consisting of the conflicts means, there itself we are making a note that, or we are concluding with a statement that therefore the given grammar is not an LR of 0 grammar or LR of 1 grammar or CLR of 1 grammar. But here what the question is, the given grammar is an ambiguous grammar, but can we create a LR parsing table for it? Yes, we can create, but the grammar, the table consisting of the conflicts, how to resolve those conflicts, and how you make that, how you are making that ambiguity as a disambiguate grammar, and finally how you are ending this with the unambiguous grammar. That means initially I am taking the grammar as an ambiguous grammar, and by resolving the conflicts, finally I am concluding that it is an unambiguous grammar, right? And why we want to use an ambiguous grammar? Here we are having a question. For such type of questions, the answer is some of the ambiguous grammars are much natural. That means the corresponding unambiguous grammar can be very complex. If we are having such type of constraints, if we are having a complex grammars, then we can choose an common natural grammars. Those are nothing but an ambiguous grammars. And usage of ambiguous grammars may eliminate the unnecessary reductions, right? These are the two most important answers for the question why we want to use an ambiguous grammar. And here we are having a grammar. By seeing the grammar itself, if you are well known about the concept of the top down parsing, you can easily understand the given grammar consisting of an ambiguity. Why? Because the left hand side of the variable is appearing two times at the right hand side, right? Is it clear? But here in bottom up parsing we are showing that we can also create the LR parsing for the ambiguous grammar, right? If it is in a top down parsing, to construct LL of 1, that is a predictive parser, then the first initial step is to eliminate the ambiguity. Initial step is to eliminate the ambiguity, and the grammar looks like this. After eliminating, the grammar looks like this. But here in bottom up parser, we need not eliminate anything. We need not perform any type of eliminations, because ambiguity, left recursion, left factorial, backtracking are all the problems of the top down parser, not with the bottom up parsing, right? So initially the bottom up parser never involves the backtrackers. So as it is, what the grammar it is, the G, as it is the grammar I am taking here, and I am implementing the LR of 0 items for this. That means I compute, initially I format the augmented grammar, and I then compute the closure of phi function, and then I gave the name it as an I naught. From the I naught I performed the go to functions by calling each and every symbol. The symbol may be a non-terminal or the terminal, and after performing the overall computation, finally I represent a table like this. And here, as the context itself, it says that if you take an ambiguous grammar, compulsory at the construction table where we get an conflicts. Compulsory we get an conflicts. What type of an conflicts that we get here? And at I7 with plus we are having reduce shift conflict, but here only we are taking a reduce. Why? Because I will explain that. This is an resolved without errors, without conflicts. It is an resolved table, and finally showing that this is an unambiguous grammar. And initially it is this entry consisting of shift and reduce conflict. This entry also consisting of shift and reduce conflict. That's why I represented with a red mark. I am showing with a red mark. And at 8 with plus is an reduce and shift conflict, and here also I am having reduce and shift conflict. What it means is here LALR parsers may introduce the reduce conflicts, but there it never introduces an shift reduce conflicts. But such type of like an ambiguity grammars always encourages or introduces an or it produces an shift reduce conflicts. How we should resolve this? How we should resolve these conflicts? See, at I7 we got the conflicts, right? At plus and star, and at plus we use and reduce. Why? Because we are having an right associativity and left associativity, and for the operators we are having the precedence operators. Which operator is having the more precedence, and we are choosing those operators. That means, and at the token of place, I am having shift reduce conflict, right? In that shift reduce conflict, if I perform left associative with the place, it is having a more priority. So that's why I am using a reduce here. And while coming to the token star, that means a terminal star. Here also I am having the conflict shift reduce conflict. And while comparing the operators, star is having the higher precedence than the plus. So that's why I am using a shift. Instead of these two, just I am using this shift by resolving the conflict. And here instead of these two, I am using the reduce instead of continuing the conflicts. So see, at 7 and plus it is R1, and at 7 and star it is an S5. In such a way, again the I8 with plus and I8 with star, here also we are having the explanation. See, I0 with E goes to I1, I1 with 5 with the star goes to I5, and I5 with E goes to I8. What it means is at I8, item number 8, at plus and star I am having the shift reduce conflicts, and here I am taking the token star. star, when I perform the left associative with the star, star is having the highest priority, so I am using a reduce operation there. And when I'm considering the plus token, that is a terminal plus, in the both shift and reduce is having a highest precedence. Why? Because star, in star and plus, when I perform the reduce operation at star and plus, star is having the higher precedence, so I am preferring the reduce here. That means in the both plus and star, here I am using two reduces. See, reduce. In such a way we can resolve, but we did not need these type of explanations to resolve the grammars at the place of constructing the parsing techniques, right? Make a note of this. Here my concept is to show that taking the ambiguous grammar and showing that it is an unambiguous grammar. So for showing that it is an unambiguous grammar, what I am doing is I am resolving the conflicts. How I am resolving the conflicts is, here I am having the explanation how I resolved. Depending on the associativities and depending on the precedence operators, I resolve my conflicts, but it is not necessary when we are implementing it the parsing techniques, right? Here, to show that it is an unambiguous grammar, I need to resolve the problem. So now I am showing that this construction table of LR of 0 is an unambiguous grammar, and this is enough for the concept of showing the ambiguity grammar to an unambiguity grammar. But at the concepts of parsing techniques, constructing the parsing techniques like an LR of 0 or LR CLR of 1 or LLR of 1, if you get such type of conflicts, conflicts at the parsing tables, no need to resolve this, and no need to give the explanation like this. What we need to do is just we need to write the statement there. Therefore the given grammar is not an LR of 0 grammar, or therefore the given grammar is not an LR of 1 grammar, or therefore the given grammar is not an LLR of 1 grammar. And why what's the reason? At action of 7 comma plus, there are two entries, that is R1 by, it is an S4, right? R1 by S4. That means reduce shift conflict occurs there. So in an entry like 7 with plus, I am having a conflict. So error. So finally it can be considered as an error. So therefore we can conclude that this grammar is not an SLR of 0 parsing grammar, or this grammar is not an LR of 1 grammar. Like that you can conclude that. No need to resolve the conflicts, because why we resolved here means here the concept is, here in the concept itself we are having an point. We can, to show, we can create LR parsing table. Yes, we can create the LR parsing tables for the ambiguous grammars, but we are having some conflicts. And by resolving those conflicts, and we can make the ambiguity as a disambiguity grammar, and finally we are showing that it is an unambiguous grammar, right? To show that it is an unambiguous grammar, we are resolving like this. But actually, as per our concepts in the parsing techniques, we need not to resolve the conflicts. There is no need to resolve the conflicts, and no need to show that the grammar is an LR of 0 grammar. If you get the conflicts like this, that means in one entry we are having two operations, then we can clearly define that here we are having a shift reduce conflict or reduce conflict. So the given grammar is not an LR of 0 grammar. In such a way we can conclude the answer, right? Is it clear now? With this I completed the bottom-up parsing concept under LR parsers, and in that the subcategorized like an SLR, CLR and LLR. And in the next class I'm going to explain the next phase of the compilers, that is semantic analyzers. And what we generated when we done this type of parsing techniques, finally we generate the corresponding parse tree from the, based on the constructed parsing table. That means after completion, after implementation of the syntax analyzer, finally what the output it is, parse tree, right? We need to generate the parse trees by implementing with them syntax analyzers. And now this parse tree is acting as an input to the semantic analyzers. And now I need to implement on semantic analyzers just by performing the type checking, type conversion and so on. and whatever the internal concepts that are included under the semantic analyzers, and I am explaining all those. I will explain all those concepts under the semantic analyzers, and I make you understand how the implementation takes place in semantic analyzers. In the next class, I will start the concept that is about an syntax analyzer.